All right, we've got a few people tuning in. All right, so for the homework number 3, double check something here. Please stand by. Looking at the I'm sorry, it's homework number 4. Let's get that posted there. And then I'm going to brush up against hopefully you are reading the through the examples. So let me kind of try to clarify what kind of understanding here. You should be able, and this will be in the review sheet ultimately, but people have asked about the make up a word here, the cumularity of the final. I did tell you I have a poetic license, so I can do that. It came with the English degree. How much of the exam is cumulative for the final? And my answer is about 80% will be on the stuff since the last exam, and around 20% would be on the biggest ideas that we've talked about, and that will be in the those will be listed in the review sheet as well. But the main idea is that it would be not so much little nitpicky details, but big ideas, understanding things like the relationship between, I think not a picky detail is that regular languages, and we're going to look at yet another category here shortly. We've got regular languages so far that are a subset of context-free languages, and now we're coming up on the next larger inclusive grouping, that those are a subset of the context-free languages, are a subset of the Turing recognizable languages. So what we've been doing is expanding on the computational capabilities, right, along the way here, of each of the machines that we've looked at. And now we've gotten to Turing machines, and we're claiming that those are able to do anything that a modern computer can do. Granted, the efficiency and we've looked at the tediousness of moving this tape back and forth. But hopefully you're starting to get the impression that you could put anything you want on those little squares, individual elements of the tape. You could group them together. You could take 8 of those little slots on the tape at a time and think of them as bytes, right? You could put zeros and ones in there, and then construct a Turing machine. And if you look at the examples here in the book, you can see it starts getting quite a few states in order to do even a fairly trivial shifting back and forth, moving the tape, looking for something, and kind of moving around. So while we can imagine that we could come up with a state machine or a full Turing machine that would do more and more complex operations, we also start to think, yeah, this is going to be pretty complex just to try and figure out all the states and moving around. So my abstraction remember for the PDAs, so we're working with those, the abstraction tool was to have just one PDA that you could translate any CFG you could translate into transitions for that PDA using the stack to push and pop right-hand sides of rules, right? To basically turn a CFG into a PDA that would handle any language, any CFG that you gave it, simply by adding transitions to that state off the end of the state number 0, state number 1. You just add transitions there, and that we relied on should have some sense of the power of that non-determinism, being able to try all the different possibilities, right? So you didn't have to specifically encode much like anything about if I see this character, then try going here, doing this. It would just go, oh, okay, I've got a rule, I've got a character I'm looking at, I've got this on the stack, I'll try this, I'll try all the things that I can possibly do at this point, and it'll end up picking, trying all the bad ones if it needs to, find the good ones, and end up getting you to the result. So it kind of manages itself when you use that approach to it. And for the Turing machine, what's the abstraction tool that I'm trying to use is kind of pseudocode, right? To say, rather than necessarily encoding all these detailed states in here, we'll say, well, move to the left until you hit a $sign, back up 1 to the, I say, move to the left until you hit a $sign, move right 1, write something, move back until you hit a £, whatever. That kind of just putting the logic into pseudocode to describe what the machine is doing rather than necessarily doing the state implementation to make those happen. Having said that, you should be able to trace a given example. Well, 3.7, example 3.7 on page 171 is a pseudocode description. And then there's a matching state diagram that goes with that basically the pseudocode on page 171 explains the workings of the state diagram on 172. Did you get caught on I-25? Yeah. Yeah, I heard there's quite a jam up down to 1 lane out of 3 actually moving or fewer.
About 25 minutes, still 1 mile.
Yeah, last week, a week or 2 ago, I got stuck with Stetson Hills thing. Yep. Yeah, that jammed up right past the last possible turnoff where I could have gone a different way. I realized what was in front of me.
Too late.
Yeah. Yes. Somebody got creative and went over the median, but it was like, big, wide, ditched median that you had to really count on your four-wheel drive being ready. Anyway, so what you should, given one of these state diagrams and an input, say, you should be able to trace what the thing is doing. Okay, so the level of understanding, I guess I'm not going to ask you to generate any Turing machine state diagrams. Okay, and that won't be, shouldn't be in the homework either. Verify that. If so, then super simple. Let's see. No, implementation level by description. So, yeah, so I mentioned homework number 4. I'll get posted out there. It'll be involving Turing machines. We'll do a little bit more work on solving some problems, kind of using the pseudocode approach. So a kind of example, a kind of problem you could expect to see might be a like on an exam or something, and I might add one for the, well, I guess in the homework number 4, number 3.8, says give implementation level descriptions. Oops, better verify what they're saying is implementation level. The idea was to give a pseudocode description on that. I'll make sure that's clear in the assignment. Anywho, so coming up with a description that says, here's what I would do to, like what we did last time for adding 2 numbers together. So it wouldn't be adding 2 numbers together, but that same kind of description of how would you approach it, being able to describe it in a pseudocode level way so that you can tell. And we'll do some more examples along the way here before we get too far. But I want to focus on some of the implications and the questions about, well, are there other things you can do to a Turing machine that would make it more powerful? And so around page 176 is where it starts talking about some variations, such as multi-tape the multi-tape one more powerful? Like, do you need more than one infinitely long tape to do some problems? What do you think? Oh, right. I mean, if nothing else, go 2 gajillion squares to the left and start your second tape there, and go another 2 gajillion past that to start your third tape if you're doing a 3-tape machine, right? So would a 3-tape or 4-tape or 8-tape machine possibly, would it do any more complicated problems? Could you solve more things with multiple tapes? No. Could it possibly be more efficient?
Oh, no.
I mean, if you don't have to move a gajillion to the left or gajillion to the right, that could speed things up a little bit. But as far as kinds of problems that you could solve, it would make no difference. So theorem 313, every multi-tape Turing machine has an equivalent single-tape Turing machine. And they go through a essentially a construction where You just mark off spots on the tape to represent the 3 tapes, right? And the only thing you have to add to your instructions. So this is a resounding no. And so, these are should be somewhat intuitive. What about deterministic? Is that more powerful?
Sure.
I don't think so. It might save you some states though.
Yes, right? Like an NFA. Similarly, due to the similar to an NFA and a DFA, right? We saw those were the same in power, but could be a little more. The NFA could be somewhat simpler because it's leaving off detail of what would have to happen in terms of the deterministic. Instead of going to a dead state, the NFA just runs out of places to go and just says, okay, I can't go any further, I quit and don't accept or whatever. Or it says I have characters left over, so and I stopped, and so I don't accept. So the answer is non-deterministic Turing machine turns out to be no, not more powerful. And how can we justify that? Can you put my mail down so it's not bleeping? There we go. What do you think? Did someone attempt why? Based on what non-determinism means.
You could just have a deterministic machine that hard to take all the possible paths. The non-deterministic.
Right. It's sort of, I mean, in a vague way, put a big loop around it and have it keep trying. If it fails at this time, if you get to the fail state, have a transition that takes you back to the start, and resets and keep track. Put a little marker somewhere on your tape, right? You can always do that and say, this time, wherever there's a choice, go down the other path or something like that. So just like if you were coding it, ask yourself, how many of you write or commonly write non-deterministic programs in your coding? Not in the sense that we've been talking about it, right? Not in the sense where it'll automatically try all the possibilities. I mean, you might have to, in the algorithms class, we call that, what do we call it? We call it the brute force method or the exhaustive search method, both of which essentially mean the same thing and mean try all the possibilities, right? So you have to do it yourself. You have to code it up yourself. So it's not too much of a stretch, I think, to see why non-deterministic is kind of our, we use the term, we use it in kind of a theoretical sense with the machines that we have, and we say they just try all the possibilities. If you're going to actually code that up, you'd have to have it try all the possibilities, right? So kind of from that sort of intuitive, common sense approach, you can make your, since you could write code to do it, you could make your deterministic Turing machine try all the possibilities itself. So basically coding in the non-determinism. So again, the theorem. So I state the theorem. I was flipping pages. Theorem 313 is that every multi-tape Turing machine has an equivalent single-tape Turing machine. Basically answering the multi-tape question. And then the question of non-determinism is theorem 316 on page 178. Every non-deterministic Turing machine has an equivalent deterministic Turing machine. And the example he uses, or his proof, is a construction proof where you basically have the deterministic Turing machine simulating the non-deterministic one. Or basically what we said, try have a machine on the outside that runs the non-deterministic or emulates the non-deterministic one, taking all the paths and keeping track of, we went down this possible route, we went down that possible route. And so imagine it would be somewhat tedious, but certainly within the capabilities of our basic idea of computability. I skipped a definition back on 170, which was these are important. Because it's going to, we're going to come up against it here. Oops. Can't talk right at the same time. So we have to define what we mean. So when we, I'm reading out of the book here on page 170. Usually I say I'm not going to read the book to you, so this is one of those little exceptions. When we start a Turing machine on an input, 3 outcomes are possible. The machine may accept, reject, or loop. By loop, we mean that the machine simply does not halt. Looping may entail any simple or complex behavior that never leads to a halting state. So a language is, a Turing machine will have an accept state and a reject state, at least one of each, and a recognizable language means that start here. So if we feed an input into a Turing machine, it can have one of these three possible outcomes. Turing machines that halt on every input are called deciders. They always make a decision to accept or reject. Or so we say, if a machine that will always stop and recognize some language is said to decide that language. So a language is Turing decidable if Turing machine decides it. So right off the edge. Okay, so these are both off of page 170. Let's see. These might be kind of like. I don't hear any gasps of surprise or excitement yet.
What do you mean by always stops?
That's the definition of what decides means. So that means it accepts or rejects, but does not do this. And false. I should say, and always. False. Okay, so there's an ambiguity or an unknown nature to the recognizable.
That's debatable?
If you give it, how so?
You said that's debatable?
I said it is, what did I say? It sounded like a good thing to say, but I don't think that's what I said. I think I said,
Decidable?
oh, decidable. It is, a language is decidable. Can you think of any machines that, or any languages that for sure would be just Turing decidable that we've seen? It's been a long 10 weeks, I know, but could you emulate a DFA on a Turing machine? Hint, did you have to emulate a DFA using your computer? Sure, right? So an example of a Turing decidable language might be what? Any of the regular languages. Right, because you can tell if a string is in a regular language or not in a regular language. Right? Just make your Turing machine pretend it's a DFA, and you got the answer if it's a regular language. Can a TM emulate a PDA? I would certainly hope so. Where does the stack come from? Pick a slot somewhere on your tape, right, and call that your bottom of the stack, and then just keep building on from there, pushing and popping stuff off by moving the tape around. Just make it work like a stack. If you feed in a string to a PDA, like what we did that's recognizing a context-free language, will it stop? I certainly hope so. Right? It'll stop on either running out of input, or if it can't run out of input, it'll stop when it can't do any moves, or when it runs out of stack gets emptied out. Right? There's lots of ways for it to stop. And it's guaranteed that it's going to try all the possibilities, but there's a finite number of possibilities, so it will eventually stop. There's a finite number of rules in a CFG, and so there's a perhaps large but finite number of different combinatorial choices that you could take to apply those rules, right, on any given string. And that's going to, and for the example certainly we do, that's going to be a fairly small number of choices, and you're eventually going to end up running out of choices and either accepting or rejecting. So would a CFL, context-free language, be Turing decidable? Sure. So the troubling one, what is the problem with a Turing recognizable one? What's the difficulty here? Can't really tell if it will stop or not. With a Turing recognizable, if the string is in there, in the language, it will eventually stop and accept it. That's by the definition of recognizing it. So it can accept strings that are in, and it can reject strings that are not in. The big question is, when it's running for a while, how do you know whether will it ever stop or not? And the answer is you can't tell. And that's going to lead us to another whole kind of philosophical kind of problem about what the limitations of a Turing machine are. Okay, so we did need definition of Turing recognizable and Turing decidable. So decidable, we've got the Turing machine sitting there, and I wanted to point out, this is not related to a totally different and unrelated topic. Not stopping. So have any of you ever written an infinite loop? Sure. Right. Very easy to do. Ever left off the variant element in your while loop, the thing that's supposed to change, right? Yeah, I did that actually fairly recently. Like, oh yeah, I was going to put that in there. It runs for a while, and you don't know whether it's going to stop, but you think, I should have taken like 2 seconds, and it's still running. Better stop. Better put it on the debugger. So what we're not talking about here specifically, we're talking about the nature of a language and the nature of the Turing machine, but not like, oops, we could have written it so that it would stop, but we goofed up and we made it and it doesn't stop. So that's not the issue at hand. Right? Okay, so we're talking about some languages. In the nature of the language itself, you cannot make a Turing machine that will decide it, that will always stop. And that's totally different, right? So just that can be confusing. It might be easy to kind of look at it. I'd say again? Right. We don't know if it'll ever get there, but it's due to something inherent in the language that, well, we just really can't tell whether it will stop. And that's going to bring us into, well, is there a way to solve this problem? Is there something we can do that we can go, we can identify in this case that it will not stop. When we're dealing with those kind of definitions, we're really talking about, for example, would it ever be possible, we're not, sometimes as you're seeing this, you kind of go, wait a minute. I can think of a counter example, right? Can I ever tell if a Java program will stop? Can you conceive of a Java program that you could write, you could always guarantee that it would stop? Think simple.
Yeah.
Yeah, sure. How about a system.out.println 5 or hello world? Yeah. Can you guarantee that would stop? Yeah, pretty much. You can look at it and you could emulate it. You could look at the rules of proper construction of a Java program. You can look at the CFG for Java and come up with the fact that there is no repetition going on. There's no, it's pretty much, you can count the machine instructions and see that they will always execute in, assuming again a correct compiler, right? So we're taking out any error factors, and so certainly you could come up with an example of, I could tell if a particular instance of a program could stop. What we'll be expanding on here and what we're talking about even with this Turing recognizable is not can you ever create a TM that you could look at it and recognize and tell that it would halt. We're not looking at the one case, we're looking at the general case of, can you solve the general problem of, you give me any Turing machine and I can tell whether it will halt or not. And that's what kind of our next topic is going to be into. We're flipping into the chapter 4 and the whole question of decidability. So we're still going to come back and do some more Turing machine examples, but to kind of introduce and start down the topic, I wanted to discuss some of the question of decidability. Can a language, can a problem be decided. Deciding means it'll always stop. If I run an algorithm, the algorithm is guaranteed to stop, and it'll either give me a yes or no answer or an accept or reject answer. Why should you study undecidability? Showing that a problem is unsolvable doesn't appear to be of any use if you have to solve it. So there are two reasons. First, knowing when a problem is algorithmically unsolvable is useful, because then you realize that the problem must be simplified or altered before you can find an algorithmic solution. We'll talk some about two classes of problems, one of which is solvable in what we would call reasonable time or polynomial limited bounded time. And then those that are not limited, where you have to basically, it's non-deterministic polynomial time, and you can, in polynomial time, you can figure out whether you got the right answer, but to find the answer, you have to try all the possibilities, basically. It's non-deterministic, and so you have to look everywhere. As soon as you start having to look everywhere, you're talking about a problem that is intractable and that is potentially unsolvable in any reasonable amount of time. So let's, we can start enumerating decidable languages. So I just alluded to the idea of DFAs, NFAs. So over on page 194, just want to start talking about recognizing some justification for some decidable problems. Call it. Call it. Yeah. This way. Okay, so it may not feel like it, but these are actually some problems that I was just talking about, that we already have seen. Yeah, we can come up with an algorithm, like if I have a DFA, it has a fixed way of working that we can apply that, and we're guaranteed that it's going to always stop. So it's decidable. So whenever I'm using decidable, you want to think, right, the key here is it's always going to stop and give you an answer. Shortly, we're going to look at some problems that are not decidable, and then things get interesting. So acceptance by a DFA so the shorthand this little ADFA, we're going to use his notation that he uses multiple times here. So the big letter A means acceptance, and the subscript is the particular problem or machine that we're talking about. So acceptance by DFA is decidable. What's the justification for that? Well, I kind of walked down that a minute ago, right? Just emulate it on a Turing machine and have the Turing machine exactly work like a DFA. So when it gets to the end of the it's going to, on each input element that you put the input string onto the tape, you have encoded in your Turing machine a set of states that emulate the DFA. And so every time you move the tape one slot, you do a transition that corresponds to the DFA. Right, so you're basically emulating the DFA with the TM is the proof. So page 195 on an input B with W. So you're going to see the problem. We're taking the input so the argument goes, we're going to, for the Turing machine, we're going to take as input a DFA, we'll put that on some encoding on the tape along with an input string. Just have to put markers on there so we can find our way around, right? And then emulate the DFA. If the simulation of the DFA ends in an accept state, say accept. If it ends in non-accepting state, then reject. So we're formulating it a little bit different. We're giving it a DFA, handing the TM in some encoding, right? We could come up with any way that makes sense. It could be anything you can imagine that you would do with Java or any other programming language. Give it the DFA, give it the input string, run the states, go through the states of the DFA, and if that DFA stops in an accept state, then put out the Turing machine halt message accept. Otherwise, if it ends up in a non-accept state, put out the Turing machine will say reject, and it's done. Okay, I'm not going to go into as much detail on further ones. What about? Let's see how much room have I got. Oh, we're almost. Oh, lots of room. How about acceptance by an NFA? Decidable or not? What do you think?
Yeah.
Sure. You can emulate it, right? You could write a program that did it. It would just try all the possibilities. Or what's the other way you could do it?
PDA.
We could do a PDA. I was thinking downsizing, downscaling. We could convert it to a DFA and then run the DFA and get the answer back. So we have the algorithm to convert the NFA to a DFA. We went through that. So there's a couple of definitions here as we're going along that you'll have to keep in mind, and one is decidable, means it always stops, for lack of a better detail. And it will always say accept or reject. So it's going to stop and it will give one of the two answers. And you should have some idea of why we can justify this acceptance by DFA is decidable. Because we can just emulate the DFA, we know the DFA will stop. Same with the NFA, I can convert it to a DFA and then run the DFA thing from here and tell that it will stop. How about determining whether a regular expression generates a given string? So we take a regular expression and we give a string, and we can say, what did they use? Rex. Acceptance by regular expression. Well, these are all related, right? I mean, they're all regular languages, so you would expect that by converting, you could argue that, well, regular expression can be converted to an NFA, an NFA can be converted to a DFA. So we're kind of building on what we already know and saying, I can tell whether a string can be generated by regular expression. And so that is decidable. Pushing ahead, a couple more here. This is empty. How does he? So this is telling whether DFA is an empty or accepts an empty language. In other words, so if the language has no strings in it, can we tell that? Can we tell whether the language for a DFA is empty? How can we tell? Well, now we're not saying does it accept the empty string, but does it have no strings in it whatsoever? So we're not saying we're not just asking the question, is Q0 accepting the empty string? We're not asking that. We're saying, does the DFA accept any strings? How might we go about that? We got the DFA description. It's got transitions on it. Remember, for every element of the alphabet, every symbol. Can it ever accept any strings at all? So here's an example, right, of so here's an example of a DFA that never accepts any strings. The language for that contains no elements, contains no strings. I would say this is the same as null. enumerate. Well, we basically do a, let's see, who has had algorithms already? Anybody? Oh, okay, taking it. So if you're taking it now, what would you use? What are you looking for? It's a directed graph, right? A DFA is a directed graph. So you could do a, you could enumerate all of the except states if they exist. So if there are no except states, then the answer is the language is empty. But if there are some except states, then all you have to do is find out whether there is a path from the start state. Do a, if you had to, you could do a breadth first search or a depth first search. Wouldn't make a whole lot of difference in this case, but you could go through and find out, can I reach any except state from the, just looking at the edges, right? We don't have to worry about the labels on the transitions, but if I just follow the arcs, can I get to an except state and then answer yes or no by that. So as your book talks about it, mark the start state of A, repeat until no new states get marked. Mark any state that has a transition coming into it from any state that is already marked. That sounds kind of like a breadth first search. If no except state is marked, accept, otherwise reject. So basically, right, a simple search starting at the start state, going everywhere you can go on arcs. So if you had something like, just to finish this guy out, if you had an except state like that, and this whole thing is your DFA, then you can't reach the except state. Even though one exists, there's no transition to it. So would that be a valid DFA? Could you have a DFA like that? By the definition of DFA? Oh. How about now? Right, so the rule on the DFA is that every state must have a transition on each input symbol, each alphabet symbol. But there's no requirement that says that it even has to be connected, a connected graph, right? So it could have this situation, and right, this is start. And so in the kind of simplest example of a weird empty language, you might have an except state, but it would be wrong to simply say, look at the definition of the DFA, and if there are any except states, then answer no, the language is not empty. Right? So you need to have except states. If there are no except states, then clearly the answer is yes, empty is true. But even if you have except states, you have to follow the arcs and make sure, do a search to find out that there is no path that can get you from the start to the except state. So let's see. Yeah, so even Dijkstra's algorithm could be employed here to look for all possible ways to get to an except state. Okay, now here's a tricky one. And one that, first one that, I mean, these are all pretty plausible, pretty easy to accept. How about equality of two DFAs, or equivalence? So on page 197, determining whether two DFAs recognize the same language is the issue. Asking the question, if two DFAs accept the same language. Is this obvious and trivial? Or is there a little more challenge to it? Think for a second about this. Do two DFAs have to that accept? Okay, so some questions that would be nice little thought questions for an exam, say. Just for example, did two DFAs that accept the same language have to have the same number of states? Nah, because you could have any, I mean, thinking of sort of the maybe malicious example would be you can just have a bunch of little accept states or something dotted around here, some of them connected, some of them not even connected, right? There's nothing that says that a DFA even has to have all states reachable or all states reachable from the start. So the answer is, so two DFAs that accept the same language may not have the same states. Two DFAs that accept the same language, would they have to have a correspondence between the accept states and the non-accept states? In other words, if you're trying to compare numbers, right, you could say, well, this has Q1 accept and this one has Q1 not accepting, so they must not be the same. Well, there's no standard, right, regarding how you number your states, so you could have them arbitrarily different in that regard. And you could even think of more complicated examples where it may not be clear that the path through, if there's 25 states that are all actually reachable, to tell whether that one is exactly identical to another DFA. Maybe the person was real sloppy in creating their DFA and they have lots of extra states in there. They didn't see the little trick somewhere, and so it's entirely possible that the two DFAs don't have any of the same typography or the same topology is the word. They may not look the same. They may not have the same nodes and edges in the graph. So how do you do it? Introduces the idea of, and you're not responsible to memorize this, but you should understand what it is saying. It's essentially this. We'll stop here with this last idea. Here is L1 Venn diagrams, right? So the union of L1 and L2 would is represented by what part of this graph? Yeah, everything that's inside the circles, either circle, both circles, right? The union would be sort of the outside, everything inside there. What's the intersection? The intersection is there. And so if we look at, let's just walk quickly through on page 197. We are going to make a new, we're creating a new language that consists of everything that is in L1 or language A, everything that's in A, or not B. So let me read. This is A, B. So everything that is in A and not in B. So that would be everything outside, right? In A but not in B. And everything, one second. Reading across. So this is the intersection of A with everything that's not in B, union with everything that's not in A, intersected with B. So if you look through that for a few minutes, the idea is if that is empty, if LC is come on. We're going to construct the DFA to accept C. So we know how to do union on two DFAs. So if we have two DFAs, we can build according to this little equation here. C is the union of language from A intersected with not B. So we can construct a DFA for the complement of B, right? Just flip all the accept and reject states. We can intersect those by doing that algorithm that we did to construct intersection. And on the other side, we can do one that is not A intersected with B. Build that DFA, and then we can take the union of those two. And the whole thing is to construct ultimately a DFA that is what this is called the symmetric difference. And so, yeah, it's getting past the maybe what you really want to think about deeply here. But if you look at it, give it a few minutes. The idea is if the result C is empty, then if C is empty, then the languages are the same because you're taking the symmetric difference. So the difference between them. So we just said we can find out if DFA is empty or not. So we build this complicated DFA called C. We apply empty to it. And if the result is empty, they are the same. And if the result is not empty, then they are different. So this is all to argue that we can tell whether the languages of two DFAs are equivalent. How? By doing a construction of this convoluted symmetric difference. Strictly by, we can do all those steps, right? So way back there when you're doing intersection and union and everything with DFAs, we're we could pull that forward. We have the justification and say, okay, it's reasonable to think that we could build that combined DFA using a series of constructions off of the DFA for language A, DFA for language B. We come up with this combination of the two to create DFA C, and then we can check it for empty. So that's where we stop. That's where we stop for today. Yay. All right. Oh, this is the end of our week for our class, isn't it? So have a good weekend if I don't see you tomorrow.